All right, so today we'll talk about subset sum, but it's going to build on what we've been doing. You might have forgotten, but we started looking at these SAT problems, these simple logical problems. Uh, and we started asking a different kind of question, whether even this has a polynomial time algorithm, right? I give you some formula, and you want to know if there's some satisfying solution. Does it have an algorithm or not? And Uh, the surprising thing is that not so much, well, A, we don't know if there's an algorithm, but two, we start looking at special cases, related problems, and showing they might not have an algorithm either. But in a very strong sense, there's going to be an algorithm, for example, for CNF-SAT where it's in conjunctive normal form, if and only if you can do all Boolean formulas, right? And we start showing that, oh, these problems that you might think were easier are actually justifiably hard, right? It's the justifiably part that I think is kind of unique. Same story for 3-SAT, circuit SAT, right? We don't have algorithms for any of these, but we know that if you have one, you get all, right? Which is an interesting dynamic. We played a similar game with 2-SAT and max 2-SAT, right? And one thing kind of fun, they look very similar. Still, you can ask the same question, does each one have an algorithm? And they ended up having very different outcomes. So 2-SAT, we came up with an algorithm solving this in linear time, right? Where actually you start thinking about this implication graph and what does it mean? What does it mean to be a strongly connected component? Things like this. And then you can actually kind of outcomes a very fast and sort of intuitive algorithms. Whereas max 2-SAT can actually be shown to be hard, just as hard as Boolean SAT. We, I think, went from 3-SAT, but you have to come up with this incredibly clever, sometimes we call these gadgets. Yeah, trying to convert one 3-variable clause into a family of 2-variable clauses. Yeah, and this was quite detailed. This is not easy to see going forwards. I feel like we can barely verify it in hindsight. So this is quite clever. Okay, but in this way, we showed that max 2-SAT, in fact, is just as general as solving any Boolean formula as far as getting an exact algorithm in polynomial time goes. Okay, so today we're gonna, yeah. Sorry? Oh, good question. We actually haven't shown that if you can solve SAT, you can solve max 2-SAT. Yeah, that we actually don't know. It is true, but for the first family, just SAT, 3-SAT, Boolean SAT, that one's a little bit simpler because Boolean SAT just generalizes SAT. You're right. You're right. So actually, we don't know that. Yeah, it's still within possible. It's quite possible that max 2-SAT is even harder, right? Although that seems counterintuitive. Yeah, that's true. We haven't done anything else. Okay. So right now we're just taking as a premise that Boolean SAT, just any Boolean formula, that ought to be hard. Anything that solves it is sort of our definition of hard at the moment. Okay. But we'll do sort of a elementary problem today called subset sum, which you've encountered many times, right? So in the old days, we had a currency, a fiat, which had coins. Yeah. One was worth 25 cents. It was called a quarter. Another was worth 10 cents. It was called a dime. There was a nickel worth 5, and a penny was worth 1. And the units were called cents. Yeah. So if I said 93 cents, and you have to break it down into these coins, what would it be? All right, 3 quarters, 1 dime, 1 nickel, and 3 pennies. Yeah. Okay. No big deal. Okay. So, but that's basically the problem we're looking at in some sense. So, your input is going to consist of a bunch of integers. We'll call them x1 to xn, and a target value I'll call t for target. And the question is, can you find a subset of these numbers that add up to t? Okay. So here is, I guess, an example of a set of numbers, 14, 13, 17, 17, whatever. And your target is 52. Question, is there a subset of these integers that adds up to 52? There is? 13, 17, 18, 4, 22 plus 30, that's 52, I think. Anyone get anything else? All right. Okay, well, one solution is good enough. Okay, all right, our usual vote. So for this problem, you can either say we're going to get a good algorithm for it, or we'll find out it's going to be just as tough as like Boolean SAT, or you can not vote. Yeah? Okay. So who's not voting? Because you love not voting. You're going to vote. Okay, everyone's voting. Okay. Who thinks we'll get a polynomial time algorithm? 1, 2, 3, 4, 5. Okay. And who thinks this is going to be just as hard as SAT? 1, 2, 3, 4, 5, 6, 7, 8. Is that everyone? That's amazing. Okay. All right. Okay. So, but there's no consensus. There's a little more in favor of it going to be hard. All right. For anyone who thought we're going to get an algorithm, who thought any ideas for how to get an algorithm? Yeah. Okay, maybe we can do dynamic programming. Okay. And then for anyone who thought it was going to be tough, any argument why? Yeah. Okay, hold that. Yeah. Okay. So the first idea that came to mind wasn't polynomials. Is that something? Okay. Okay. All right. So for ideas for algorithms, you guys already said dynamic programming. Any other ideas? Okay. So let's try that then. If we want to make a dynamic program for subset sum, we need a recursive spec. Yeah. So I'll write subset sum. And you gotta choose some parameters and a sentence. Yeah. Uh, 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 okay. So given a subset or a set of numbers S, it's a lot of S's, return true if a subset of S adds to N. Do you mind if I change N to like, I don't know, anything else basically? Uh-huh. Yeah, we can do maybe to T or okay, so that's fine. Now I want to say something. How many subproblems will this have? Yeah, so one issue here is that you might have 2 to the n subproblems. It's going to be a little tough to come up with a good algorithm because usually dynamic programming we rely on enumerating all the subproblems for correctness. All right, any alternatives that what if we use T, D? Okay, so give me a sentence and some parameters. Return true if a subset adds up to T. Okay. Any other ideas? Well, I guess this is just an integer, so you can choose any T. So a little confused. I imagine if you're trying to implement this, you might try a number, right? Yeah. Although one thing to be keep track of, in this problem, you're only allowed to use each number once, at most once. So it's not quite like the coin thing where you can use a quarter over and over. Yeah. 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 So okay. So you're imagining some kind of array of length T, and I'll put an X if it can be solved and a zero otherwise or something. But like here's the thing. Let's say you're here, and there is some number that gets you from some value that you know can be solved a, a plus xi is b or something. The only thing is you don't know if you've already used xi to get to a. So it's not clear from that information in the table that you can actually get to b. Yeah. Okay, yeah, yeah. Okay, so maybe one thing is I can say uh subset of some like kt or something, and I can return true if a subset of the first k numbers, x1 to xk, sums to t. Yeah, and this way we can at least keep track of which variables we've used or not. If we say, I mean, the natural thing is that, well, we can do the implementation. So I think this is roughly, uh, yeah, okay. So imagine this is actually parameterized by n. N just refers to the first n numbers. Let's just implement this, and then I think it'll straighten it out. So I think that's what maybe we'll try to do here, actually. Yeah. So let's say you have n integers, and you have the target value t. How would I implement this? Or some base cases? Okay. If t equals 0, then true, because an empty sum will do it for you, right? What's another base case? Oh, good point. Huh? Is empty. So I guess if n is 0, n is referring to a number of integers, then false. You want, you can say if t is less, well, yeah, I guess here we assume they're positive. So if t is less than 0, then you know it's already over. I think this is not a big deal either way. Okay, now an interesting case. How can we kind of nibble off one piece? Yeah. Oh, yeah, don't worry about array. We're just going to dynamic programming. The array will come for free. So how do we do this kind of recursively? N minus 1 or t. So that means you're probably not using xn. Oh, yeah. Yeah, we either use xn or we don't. Either way, we're going to focus on the first n minus 1. Does that answer your question from before? Yeah. Well, I think here we're just going to try to decide if you're going to use xn or not. And the other variables will be taken care of in those subproblems, right? Because the next is going to deal with xn minus 1 and xn minus 2. Yeah. Okay, so pretty simple. Yeah. So what's the running time? Sorry? Yeah, so, oh, this is the wrong one. Okay. If we use dynamic programming, right, then we're going to get NT subproblems, constant time per subproblem, NT time overall. Yeah, so there's an algorithm. Okay. All right, given that algorithm, does anybody want to revise their vote from before? Yeah. Oh, now you think it's hard. Okay. So we have one. Okay. So, all right. So we had this kind of running time, right? The only issue, right, is that t takes log t bits to write down. Yeah. So the problem is that this isn't actually polynomial in the size of the input. Okay, this may be very practical in many situations when t is small, like um uh but I could load up a t is a billion gajillion and it'll only take me 20 bits to write it down or something, right? And so yeah, it'll just explode on you. Okay, so yeah, if you have some exponential size thing, you're screwed. So does anyone else have any other ideas? Okay, I think you guys see where I'm going. So let's try flipping it over and seeing if we can show the subset sum is actually as hard as SAT. Okay. But this seems like a bigger stretch of the imagination because like 2SAT, max 2SAT, or at least max 2, they have the word SAT in it. 3SAT has the word. They seem to be more similar. The subset sum seems to be a completely different domain. I mean, we're just adding up numbers. You've done this a million times, yeah? Knapsack is very hard to do. It's a bummer. Yeah, many problems are quite challenging. Yeah. Um, but maybe also what we do here will be interesting, right? But yeah, so this is I think a bigger stretch of the imagination to try to argue that maybe we can use subset sum to solve SAT because a subset sum looks nothing like SAT. Okay. So did I write anything down here? Yeah, so that's the theorem we're going to try to prove. We're going to try to show that a polynomial time algorithm for subset sum will give you a polynomial time algorithm for SAT. Yeah, so that should be very surprising. Okay, so all right, so usual kind of setup, right? So to try to show that a black box for subset sum is too good to be true, I'll start with a 3SAT instance. Yeah, I'm not supposed to be able to solve 3SAT. We'll try to take that and convert it into a subset sum problem. So I need to somehow come up with a bunch of integers and a target value. Okay. And then when we put that into a black box, uh, that didn't quite work out. Uh, right. Um, and the black box is just going to be able to answer yes or no for subset sum, and we should be able to interpret that answer. Okay. All right. Anyone before? I mean, I reveal it on the next slide, but I still should give you a chance first. Does anyone have any creative ideas for trying to convert um, stat into subset sum? Yeah. Okay. Okay. So can we somehow do primes or some kind of like number theory, black magic, right? Is there something we don't, some amazing trick for number theory or something that we learned in algebra that can save the day? Yeah. So maybe that's possible. Any other ideas? Okay, a Boolean value for each. Okay, one sec. So you start with 3SAT. So you start with a formula. You start with a SAT formula and you need to turn it into a subset sum problem. Oh yeah. Well, yeah. Yeah. Can you have n primes and in each term will be the product? Uh, okay, so okay. So a variable maps to one of the primes. A clause maps to a prime, and a variable will be maybe a variable would be like the product of the primes for the clauses it satisfies or something. It's a little confusing because a clause could have xi or xi bar or neither. Okay, yeah. Somehow trying to get many clauses or many, but you're still mapping. Are you still mapping clauses to numbers? Yeah. So each clause becomes like a big number, but maybe the individual digits can represent different logic or something. Okay. And then what would be like the target? So maybe one thing I should mention is that just from like a selection point of view, in SAT, you're choosing xi or xi bar. And in subset sum, you're choosing to include a number or not. So whenever we're doing something where we're mapping the clauses to numbers, it gets a little confusing because here we're choosing a number or not. But in SAT, you're not choosing a clause or not. You're usually choosing whether to set a variable to be true or false. So from that point of view, it might make more sense to try to map the variables to some kind of numbers. I think that will help you go the other direction. You're trying to use subsets, SAT to solve subset sum. Yeah. Okay. Uh, I'm not sure if that's specific enough for me to give you a very good answer. If you map each variable to a power of 3, okay, so uh, yeah, but well, for what it's another thing to keep in mind is that a SAT formula may have different ways to satisfy the formula. Xi could be true, Xi could be false or something, whereas T sort of feels like there's one target. Uh, yeah. Okay, well, this one is also going to be very clever, but it was sort of suggested before, but it's sort of it slightly differently. So again, we're going to try to leverage the idea that numbers are bit strings too. Okay. Uh, and we can use many digits. You kind of knew that we would need to use many digits because for small numbers, we had a reasonably good algorithm. But the idea is that we can use each digit to sort of encode a constraint, right? So for two numbers to be equal, every digit has to be equal, of course, right? Uh, so if like this digit being equal to this value means you did something in some logic, and this digit being equal to this value means you did something, some other rule. Yeah, so we'll see. Okay, so let me first just recast 3SAT as a subset sum kind of problem, just to get us a little closer. This is not the real thing, okay? But to make it look like a subset problem, uh, I'm going to focus on the literals. Okay, so you can either choose x1 or choose x1 bar. You can choose x2 or choose x2 bar kind of thing. Those are things we're choosing. We're choosing literals. And the sets, the clauses I want to look at as like a set. So x1 bar x1 or not x2 or x3, I want to think of it as a set of three literals. Okay, it's sort of a minor thing. Okay, just kind of renaming things. Nothing too deep here. Okay, but in terms of this problem, I want to find a subset of the literals, right? In this language, I want to find a subset of the literals so that A, I take at least one literal from every clause, if I think of the clauses as sets. Okay, and B, for every variable, I choose exactly one of the two clauses. This might have been already how you thought of 3-sat. Setting xi to be true is like choosing the literal xi. Okay, but this will just make it easier in the next step when the language is more lined up. Okay. Okay. So good. All right. So now that we have that, we're going to start making numbers. Okay. So we're going to use numbers with tons of digits, m plus n digits or something, if there's m clauses and n variables. Okay. And so for some literal xj, we'll do not xj next. Okay. I'm going to have, m slots for each clause and n slots for each variable. Okay. And so in the last n is just going to keep track of sort of which thing this belongs to. So I'm going to put a 1 in the j's clause for xj. Okay. And then for the clauses, I'm going to put a 1 exactly in the clauses that is satisfied. Okay. So every clause, there's m clauses, right? I'm looking at the 10th clause or something out of m. That'll be the 10th digit from the left. Okay, so again, I'm taking this literal xj, I'm turning into a number. I'm looking at the 10th digit. If that clause contains that literal, particular setting xj equals true makes that clause satisfied, I'll set that value to be 1. Okay, and otherwise I'll set that value to be 0. Okay, so it's kind of crazy. I'm taking every literal. This is the literal xj equals true. Okay, and I'm making a massive number that's encoding, lots of information from the problem. The first m clauses, m digits, are encoding which clauses this literal is in. Okay. And then out of the last n, I'll look at the jth one and just put a 1 there to remember that this literal is for variable xj. So the last n is mostly zeros. There's always only 1. So x1 will have the first one to be 1, x2 will have the second one to be 1, the rest will be 0, so forth. Most of the information is coming from the clauses. Interesting information. Okay. Yeah. So this represents the set. Yeah, so this is doing just something superficial where in preparation for the next step, instead of thinking of like you have a formula you're trying to satisfy, I want to pose it as a problem where you have elements and sets, and you have to take at least one element from every set, subject to the additional requirement that you can't take xj and not xj. So I just wanted to phrase it in terms of taking things because subset sum is a taking things kind of problem. Yeah. SOB, like you want to find this subset of literals that sort of hits all your clauses, but also only takes one of x and xj bar for every j. Actually, we're only taking the literals and turning them into bit strings. Yeah. So, well, I wouldn't quite think of it. Yeah, it's a little bit confusing because things are turning into things, turning into things. The original problem is I have clauses and I want to make sure I take a literal from every clause because it makes that clause happy. Right. So instead of thinking of as a formula satisfying problem, I want to think of it as this sort of set hitting problem I'm trying to take elements subject to certain rules, in particular, taking at least one from every clause. And then from there, I'm going to turn it into subset sum. So this is just some intermediate version to make it a little bit easier to think about the next step. And this is where now I want to take my set version of the SAT problem and now turn into a subset sum problem. So every literal, whether it's xj or xj bar, we haven't done xj bar yet, is going to turn into a very large number that's A, encoding which clauses it's in, plus which variable it belongs to. Question? Okay, good. Since we're all excited for xj bar, it's going to be very similar. Actually, it's going to be the same thing. It's just that now you're only keeping track of which clauses contain xj bar. Okay, you're still going to have a 1 in the j slot. So exact same thing for xj bar. Yeah, okay, so what's the high level idea behind this, right? You want to make sure you want to satisfy every clause. So what does that mean sort of in terms of this numbers? You take a bunch of numbers and what should it satisfy? Yeah. Yeah, at least yeah. Yeah, good. So let's do that. Let's do that here. So uh okay, so as we map this over, we have these literals and they're mapping into these long numbers. I guess I wasn't clear about notation. So x1 will map to what I'm calling a1. A1 is the number. Not x1 or bar x1 is turning into bar a1. Okay, so those are the big numbers from the previous. It's 3 sat in particular. 3, yeah. Maybe I'll quiz you at the end where we use 3 or where it was convenient. Uh, and the idea is we want to take a set of literals, right? And we're going to think of that in terms of a sum, right? If I take some literals, then that's sort of like taking those same integers, right? And sort of the set, so to speak, is sort of their sum. And uh, we want to make sure that for every constraint, I take at least one literal, right? Which in terms of our sum, what does it say? What does it mean for our sum? Our sum must be what? Must be that ith digit needs to be at least 1. Yeah, so our big number is adding everything up. So those literals are giving ones for the CIs, right? So I want to be at least 1. And then making sure that I take at least exactly 1 literal for every variable. What does that map to in this subset sum terminology? Yeah, they should be all 1, right? So the digit corresponding to that xj's variable, towards the end, that should be exactly 1. Yeah. So okay, I think we're on the same page. Now there's only one key difference here, kind of. So on the right, everything's sort of in numerical now, right? So that's looking good. But there's still one difference from subset sum. Yeah. Yeah, it's that third line where we're saying everything has to be greater than or equal to 1. That's not exactly what we want, right? We want, well, because in subset sum, you're supposed to give an exact target and say it has to hit that exact target. Yeah. And say, oh yeah, your ith digit needs to be at least 1 isn't giving us a good exact target. Yeah, question? The digit corresponding to clause I. So I'm just like referring to the digits depending on like how it was constructed. Yeah, the index. So yeah, so yeah, just like one of these slots. This might be the one corresponding to second clause, and I'll call that the C2 digit, the digit for that one. Say it louder. We don't want to make a number that's has 2 to the n bits, because then that will be a huge input size. We haven't finished yet, if that's the issue. So we still need to come up with a target, and right now we're just kind of going through like what we've done. Yeah. And so we want to come up with a target, and so it's clear that our target for the last n digits, that should be all one, right? But the first m digits, we know our target should be some kind of greater than equal to one, but it's not clear. There's no clear t, right? Because if you had one variable, that would be fine. If you had two literals, that would be fine. If you had three literals, that would be fine. But we're getting obviously much closer, right? Just one issue. So any ideas, right? Just looking at that square, we want to come up with some kind of trick so we can turn that greater than equal into an equals. Yeah. Is it like max 2 sat? I don't think that's how it'll turn out, but you could tell me afterwards if it looks like max. But that's not, at least not how I think of it, right? So we're trying to figure out a good t, and right now there's a slight. We're really close though. Yeah. Max 2 sat and check if all the digits are 7. That might work. I think that could possibly work. So if you remember max 2 sat, there was sort of like you can get exactly 7 points if you satisfy it. And so I think that would probably work. Yeah. But unfortunately, the slides aren't ready for that. But that's actually a good idea. That's as far as I can tell, that would kind of. So just to take a step back, we're trying to go straight to subset sum. But if I had maybe sort of tried to redo the same gadget from max 2 sat, where I turn each 3 sat clause into this thing where you can either get 6 or 7 points, and 7 points only if you're actually satisfying the original one, that'll give us that exact tally of 7. I could imagine doing something and making it add up to always 7. And I think that would work. I think that would work. That's a pretty good idea. Okay. Any other ideas? Because that's not what we have on the subsequent slides. One a little more direct, I guess. Should think about, what degree of subset sum, right? So we just give numbers, we give target. So you can also create more numbers. Right? Somehow, like they should be able to get one, two, or they basically want to say something where you're allowed to get one, two, or three in that digit, but not zero. Yeah. Okay, so I look at XJ. Right now they just have one for that clause, but maybe I can make a version where it's two, or I can make a version where it's three, so that there's some way to add up to exactly three. Yeah, and I can do that for all the variables and all the clauses inside. That's not a bad idea, but I think there's one catch. So if I did that for, let's take one variable XJ, and I did it for every clause, I tried all the combinations, one, two, three, one, two, three. Well, no, you're creating huge, oh, there's also some carry. Yeah, once you start carrying it, but you're also creating a huge number of literals. For every clause, it's 3 to the I, where there's I, however many clauses it's in. So number of literals you're making is blowing up. But at least, right? Because this variable, you don't know if you want it to give 1 point for this clause or 2 or 3. The next clause, 1 or 2 or 3. If you have 3 choices times 3 choices times 3 choices, that's going to get big. Yeah. Plus, yeah, you start worrying about 3 plus 3 carries over a 2, and then now you're in a world of hurt. I guess to some extent we could have made our digits instead of base 4, we could have made it base 9 or 10 to make sure it's okay. So that could be fixed, but yeah, you somehow want to say it's okay to do 1, 2, or 3 in this slot, right? I don't mean to torture you, but this is kind of guessable, so I don't want you guys to give up. Yeah. So can you, the question was, can you somehow check to see if any of them are zero and invert that? So, I mean, one thing we should keep in mind is the rigidity of the situation, right? Because we really just have a black box where you give it some numbers and you give it a target t. And so to tell the black box, can you take these numbers and the target and, just invert it and check if it's a zero? We're not using it as a black box anymore. So I think that's cheating too much, right? Because it wouldn't really show subset sum is hard because we're doing something a little different, right? Something that's the reason this whole kind of tricky is that like subset sum seems so precise. Seems like you're just adding up numbers, and we're trying to capture something much more general, and that's part of the trip, the difficulty. Where you can add more numbers to the problem as well. You don't just have to try to figure out the magical t. Yeah. So for clause, I'll make a number that's just -1. Okay. Yeah, so we're going to do negative to negative. Okay, I think that's really close. Now, what if I just told you it has to be a positive number? Yeah, sum up to 3. But then you have to be careful because it could be a 0 and you can add 1 and 2 and get 3. You're close. You're really close. Instead of 1 and 2, so the idea is like, oh, can we add some like dummy variables so you can just raise the score? And you want to be able to you want to be allowed to go from 1 to 3. You should be allowed to go from 2 to 3, and you can just keep it at 3 and ignore dummy. But you shouldn't be able to go from 0 to 3. To what? If you did two ones instead of a 1 and a 2, then you can go from 1 to 3 or 2 to 3, but you can't go from 0 to 3. I think so. It's basically your thing, but it's just a small thing. Yeah. So I'll just make something where the CI bit is 1. I'll make 2 of these for every clause, just like a little buffer, 2 free points for every clause, but not quite 3 free points. Okay. And this way you can just pad things and get up to 3. Okay. So this is all we're going to do then. So in the green, those b's are these padding variables. Okay, so clause I add 2 copies of this 1 in the ith slot. 2 for each clause. Oh, we're worried about overflow? Oh, that's a good point. Okay, we'll do everything base. Yeah, I actually hadn't thought of that. Yeah, you shouldn't be able to overflow. Okay, good. I think I need to fix my notes. Okay, yeah. Oh, but overflow will kill you on the previous problem. So if you go from 3 and you add one more, you carry the 1, but now you're back to 0. Then you're up to 1, but you're not at 3. Okay, good. So I don't have to update the notes. Good. So overflow, you actually survive, but I kind of forgot about that. Yeah. So we just needed to add a little padding. Yeah. So that's why there's 2 copies. Oh, you mean from the previous clause? You can carry the 1? I think it's okay, but if it's really bad, we'll make a base 8 or something. I did base 4 because that seemed just barely enough. But I think if you're careful about it, the overflow won't catch any issues. Okay, does that make sense? Yeah. 2 copy, each of them are worth 1 point. There's M clauses, and for every clause, 2M plus 2N. 2 for each clause, 2 for each variable. For each variable, we have 1 for each literal. Huh? What if we had what summing to 1? So if it comes out and I haven't used any of the B's yet, then I just used the 2 copies of the B's. So maybe I should go back. Yeah, BI looks like this. So I can add 1 to the score for clause I. Oh yeah, B's are for clauses and A's are for yeah, I'm not sure what's going on, but yeah, that makes sense. Okay. Right? So that's the idea. Okay. So yeah, now we put everything together, it's reset, and then you somehow encode the whole problem in these numbers, right? It just turns out that every digit is used for a different requirement, relatively simple requirement. Like you can only take 1 of the 2 literals, or you take at least 1 from each clause. Okay, and then you plug that in, and the yes no for subset sum will map directly to your yes no for your formula. Okay, but at least for me, this gives a completely different perspective on numbers, right? And kind of the weird things about computational complexity. You can actually pack, yeah, yeah. The target value is going to be 3 for all the clauses. So 3 is the max, right? Because you only have 3 variables. But if you had only 1, you can use the 2 copies of the B's to pad you up. So you can get up to 3 if you had 1. But if you had 0, it wouldn't get you up to 3 because you only have those 2 copies. You don't have 3 of them. So you can always get up to 3. One of the what? One of the, what was the last part? One of the, a dashboard? You mean like a negative variable? Yeah, yeah. It could just be x1, x2, x3, and then you'll have a1, a2, a3. Sure. The bar? Yeah, that's like a knot. Oh, you weren't here that week. I think that was the issue. Yeah, we did. We talk about this for. I don't think you were here for all our SAT lectures. Okay. All right. So, right. But this is kind of interesting, right? Because somehow you've just taken numbers, everyday numbers you take for granted, and you've sort of packed in, a whole complex problem, and that means you could start from a Boolean formula and pack it into a subset sum problem, right? So that's crazy. Okay, good. All right, so any questions? I just have some problems loaded up for us to practice. Huh? Oh, I'm glad you asked. Okay, how are they? Okay. Yeah, there's plenty, actually, apparently. Okay, so these are all some variations of the problem, and we can all chat and discuss and have fun. Um, but like the first one's pretty classic.